Okay, so I am going to talk to you about exponents today. Hopefully this is a reintroduction, not a first time thing, but if it is, we'll make it work and we'll be practicing over the next few days to really master these concepts. So first off, when talking about an exponent, we've got a couple different vocab words. The first is that of a base, and this is the number being used as a factor. So in the expression 2 to the third, 2 is the base. And then the next is the exponent. An exponent is the number that tells you how many times to multiply the base. So in the expression 2 to the third, 3 is the exponent. And what 2 to the third means is 2 times 2 times 2. The 2's are the factor, and they're happening 3 times because of the exponent. All right, and then the next vocab word is that of a power. A power is an expression that includes a base and an exponent, so it's the whole expression. So 2 to the third power could also be read as 2 cubed. Cubed is a word that means a power of 3. And then 4 to the second power could be read as 4 squared, because it means power of 2. What they mean, again, like literally, is 2 times 2 times 2, and 4 squared means 4 times 4. You've got your base, and you've got the number of times. When we are working with these in Algebra 1, our biggest thing about exponents is we're going to give you expressions that involve multiple exponents, and we're going to ask you to simplify those expressions using the properties of exponents. And there are 5 key ones that you need to be familiar with. The first is the product of powers. So I'm going to kind of give you a numerical example to explain why the variable example is what it is, or the variable rule is what it is. So here, if I gave you 2 to the second times 2 to the third, 2 to the second means 2 times 2. And 2 to the third means 2 times 2 times 2. So how many 2's did I end up with? 1, 2, 3, 4, 5. So I get 2 to the fifth. So then think about, how are this 2 and this 3 related to the number 5 using just the basic operations of addition, subtraction, multiplication, or division? If I add 2 and 3, I get 5. That is what is happening here. So for a product of powers, where I have a to the m times a to the n, I'm going to add the powers and get a to the m plus n. So then moving to power of a power. Okay, power of a power. So I have a to the m to the n. So thinking about what this means, just with numbers, I have 2 to the third to the second. Well, that 2 to the third means 2 times 2 times 2. To the second means 2 times 2 times 2, all of that, times 2 times 2 times 2, all of that. Well, how many 2's are there? 1, 2, 3, 4, 5, 6. There are 6 2's, so this is equivalent to 2 to the sixth. So again, think about the relationship between 3 and 2. 3 times 2 is 6. So the relationship for a power of a power, a to the m to the n, is a to the m times n. A to the m times n. So next we have the quotient of powers. So again, I'm going to start by showing you mathematically. If I have 2 to the third over 2 to the second, that's 2 times 2 times 2 over 2 times 2. Using our canceling rules, I'm only left with 1, 2. So how can I use our basic 4 operations with 3 and 2 to get 1? Get 2 to the 1. Well, 3 minus 2 is 1. So here, a to the m over n is equivalent to a to the m minus n. So it's always kind of like back, using related operations, kind of moving backwards. So quotients of powers, quotient means division. Division's kind of like the big brother of subtraction, because it's multiple subtractions. And then product of powers, product means multiply, and multiply is kind of like the big brother of addition, so because it's multiple additions. So they're related in terms of operations. All right, so then the next one is a 0 exponent. So if I have a to the 0, it's always going to be 1, because it means that it's not happening. So you still need a placeholder. It's not meaning it's equivalent to nothing. It just means there's no number affecting the problem, and a number that doesn't affect the problem when we're talking about multiplication or division is the number 1. And exponents are multiple multiplications, so that is why that is 1. All right, and then finally a negative exponent. I have a to the negative m. This becomes 1 over a to the positive m. It's like an inverse operation almost. You think of it like, hey, I'm unhappy, so I have a negative attitude. So now I'm going to move from the numerator to the denominator. Now I'm happy, so I'm positive. I changed my exponent. And you could flip this around and say you started with 1 over a to the negative m. Again, I'm unhappy where I'm at down there in the denominator. I'm going to move upstairs to the numerator. So now I'm happy. I'm going to change my attitude from a negative attitude to a positive attitude. So my exponent changes from negative to positive. So those are kind of the basic rules. You may consider making flashcards of those rules, making sure that you understand exactly what they are, because you're going to need to be able to use them backwards and forwards as we progress. All right, so looking at each example, looking here at example 1, I have negative 3 times 1/5 to the 0. So first thing I'm going to do is think about the order of operations, think about those 5 exponent rules. Okay, this is clearly using that 0 exponent. Okay, it's using the 0 exponent. So I'm going to do that first because of order of operations. Okay, PEMDAS. Okay, parentheses, there's nothing to do inside of it. Exponent before multiply. So I'm going to start with this 1/5 to the 0. Well, anything to the 0 power is 1. So this is negative 3 now times 1. I'm not simplified all the way yet. I can do that multiplication. Negative 3 times 1 is negative 3. And that's it. I'm done. All right, so then moving to number 2. Okay, I have 6, a to the negative 3, b to the 2, c to the negative 2. So I've got 4 different bases. Okay, none of them are the same. So it's not product of powers because those are both a. It's not power of a power because I don't have 2 exponents next to each other. It's not quotient of powers because, again, I don't have 2 of the same bases. I also don't have division. It's not 0 exponent because I don't have a 0. So this is an example of a negative exponent problem. So when I go to simplify this, I'm just going to take away the ones that are negative or do something with the ones that are negative. So the 6 stays where it is and the b stays where it is. They're happy in the numerator, okay, but the other 2 want to move downstairs. They want to move to the denominator. So it's going to be a to the positive 3 and c to the positive 2. So I've now simplified it because to simplify means I only have one of each variable. I only have one constant or one coefficient, I guess would be the better answer, the number, and I have no negative exponents. All right, so then moving to number 3. I have 3a over b all to the negative 3rd. Again, I don't have any like bases, so it's either going to be a 0 exponent or a negative exponent. Okay, could also be a power of a power, because I have that exponent up high up there. So thinking about that power of a power, I could rewrite this as 3 to the 1, a to the 1, over b to the 1, all to the negative 3. So now I've got 2 exponents like in power to a power. I have an m and an n. Okay, so I can use the power of a power rule to get 3 to the negative 3, a to the negative 3, b to the negative 3. Well, now I can see I have tons and tons of negatives. So this is also a negative exponent problem. And I can rewrite it such that they're all happy by moving them to different places. So that 3 to the negative 3 is going to move to the denominator. A to the negative 3 is going to move to the denominator. B to the negative 3 is going to move to the numerator. And when they move to each of those places, their exponent changes because they change location. Okay, because they change location. And there is one more thing I can do to simplify here. Okay, 3 to the 3rd is something we can evaluate. We can find that value. And I get b to the 3rd over 27 a to the 3rd. B to the 3rd over 27 a to the 3rd. Okay, so that used 2 rules, power of a power and negative exponent. All right, moving to number 4, a to the negative 1/3 over 5. So it's not product or quotient because, again, I don't have any like bases. It's not power of a power because I don't have an extra exponent anywhere. It's not zero exponent, so this is another example with a negative exponent. That a to the negative 1/3 isn't happy where it's at. So it's going to move down to the bottom with the 5. The 5's not moving. It's happy. Okay, it has a positive 1 understood exponent. Okay, so it's not moving. And then I can't just leave a fraction like that. I have to put something on top, and I put a placeholder in of 1. If you're feeling behind, pause the video, get caught up, maybe listen to an example again if you need to. All right, so now looking at number 5, I have 2a to the second, b to the fourth, c, times negative 3a, b to the second, c to the 0. So this one, looking back at our 5 rules, is using product of powers because I've got 2 of the same base. I've got 2 a's, and I also have 2 b's. And I also have 2 c's. It's also an example using that 0 exponent, so we might have to consider that as well. So I think the easiest way to do a problem like this is to group the terms or the pieces together. So multiplication is commutative, which means you can reorder it. So I'm going to reorder it so that the coefficients are together, so that the a's are together. I'm going to go ahead and add a power of 1 to that second one so that the b's are together and so that the c's are together. So then when I go to use my power rule there, I'm going to add my powers because if I were to write this out, A, I get 3. I add them, so I get a to the 3. If I were to write this out, b, I get b to the 6th. You don't need to actually write it out because now we know to add them. And then the 1 and 0 just makes 1, which is understood. I don't have to write it. Then what do I do with these numbers right here? Well, it's just 2 times negative 3. I know what 2 times negative 3 is, and I think you do too. It's negative 6. Now you might be thinking, oh no, there's a negative, I need to do something else. That negative 6 is not a negative exponent, it's a negative coefficient. Negative coefficients are fine just where they are, so it'll stay. All right, looking at number 6. Okay, very similar problem, just fewer components. Okay, so it's another one. I'm in that same category. So I'm going to, again, group my coefficients and then group my g's. Okay, I know and you know that negative 5 times 4 is negative 20. You now know that you can add the 3 and the negative 4 to get negative 1. Now this one is a case where you're not done because that negative 20 is fine because a negative coefficient is okay, but a negative exponent is not okay. That g is not okay where he's living. He wants to move. Okay, so I'm going to move him to the denominator and change his power because now he's positive, he's happy where he moved to. So now he has a positive power of 1, and I don't have to write a positive power of 1, so I'm just going to leave it there. All right, moving to number 7. So this one is a combo. So you've got an x in both, so you're going to be adding powers at some point. Okay, but you also have this extra power up here. So it's a power to a power as well as a product of powers. So it's both of them. So again, because of the order of operations, PEMDAS, I have to do what's inside parentheses first. Well, there's nothing to do inside the parentheses. Okay, so then I have to do an exponent. So I got to do that external exponent first. I have to deal with that 4. So I'm going to bring down this x to the negative 2, but I'm going to give out this 4. Well, there's a 1 here and a 1 here. So when I give out that 4, I'm giving it out 3 times. I get 3 to the 4, I get x to the 4, and then on that y, I'm taking 1/4 times 4. And 1/4 times 4 is 1. So now if I group it like I have on those previous questions, the coefficient, 3 to the 4, group the x's, and there's only the 1 y, so I can leave that there. Okay, I can find out what 3 to the 4th is. So 3 times 3 is 9. Okay, and 3 times 3 is 9 again. So 9 times 9 is 81. Because I did 3 twice. Together makes 4 of them, so 81. Then the x's, I can add my powers. So I get x to the 2, and then just bring over that y. All right, number 8 is another combo problem. Okay, I've got these outside powers I got to deal with first. So I'm going to give out that 5, and I'm going to give out that 3. So I get 2 to the 5. I get a to the 3 times 5, which is 15. Okay, and 2 was just to the 5 because it was 1 times 5. All right, then that negative, okay, I need to put that negative in parentheses. So I get negative 3 to the 3, and then I get a to the 3, and then I get b to the 1. So y is negative 3 to the 3 because it's 1 times 3. Y is a to the 3 because it's 1 times 3. Y is b only to the 1 because it's 1/3 times 3. All right, so I'm going to group my numbers, and then group my letters. And I meant to switch colors, but that's okay. All right, well, I can't put this 2 together with this 3 until I get rid of their exponents. So I need to find out what each of those are. So 2 to the 5th is 32. Negative 3 to the 3 is negative 27. Okay, my a's I can go ahead and put together, a to the 18, and my b is just b. All right, 32 times negative 27. I can still do something with that. It's not as simple as possible yet. So when I do something with it, I get negative 864, a to the 18, b. Again, a negative coefficient is okay. I don't have to move that. That's my answer. All right, moving to number 9. Okay, see those like variables? There's an x on top and on the bottom, y on top and bottom, z on top and bottom. So this is quotient. Quotient is subtraction. If it helps you to break it up, x to the 2 over x to the 1, y to the negative 1 over y to the 4, z to the 4 over z to the negative 3. I don't know if it helps or not. You could also maybe write to the side what you're subtracting. So like here I'm doing 2 minus 1. Here I'm doing negative 1 minus 4. Here I'm doing 4 minus negative 3. Sometimes it helps me to see that double negative there. Okay, so I get x is to the 1. I get y is to the negative 5. And I get z is to the 7 when I simplify each of those. Okay, but that's not the answer because I've got this unhappy y in here. So x is more simple if I don't write the 1. Y is not happy, so he's moving. Now he is happy, so change it to a positive. And then z is good just where he is. So x, z to the 7 over y to the 5th is the solution. All right, last example. Okay, so you could simplify inside the parenthesis first or not. It doesn't really matter. It does maybe make steps less. I'm not sure. You can kind of approach many of these different ways. I'm going to do this one without simplifying first, but by giving out that negative 2. So hopefully you see that there's 4 little things in there, 4 exponents that are going to get that negative 2. So I'm going to get 3 to the negative 2. I'm going to get y to the negative 1 when I multiply. Okay, I'm going to get 4 to the negative 2, and I'm going to get y to the negative 2. So that top y is the only one that gets the negative 1 instead of a negative 2, and that's because it had that half. All right, so then I've got a whole bunch of unhappy people, so I'm going to move them all to make them happy. So now I've got 16 from 4 squared. I've got 9 from 3 squared. And for that y, I've got to do 2 minus 1. So I just get y to the 1. So it's 16y over 9. All right, so I tried to show you a little bit of everything, a little bit of division, a little bit of multiplication, all the different rules. But again, we're going to spend quite a bit of time, 4 full days on this. So hopefully by the end you're feeling pretty confident. All right, have a great